All right, so this is our introduction to nuclear chemistry. This is chapter 11. And nuclear chemistry is completely different from anything else that we've done so far, with the exception of chapter 2 material, which talked about what the atom looks like. So I don't want you to forget everything that you studied from chapters 3 through 10, because obviously that's going to be on this last exam for chapter 10, and it's also going to be on the final. But I want you to reach your mind way, way back to when we talked about the structure of atoms in chapter 2. When we talked about the structure of atoms, we said that atoms have a really dense middle where all of the mass is, and then on the outside we have this lightweight, mostly spacious cloud. Do you guys remember this? And we had 3 particles that we tracked. We talked about electrons and protons and neutrons. Can you guys help remember? Do you remember at all, like, where these things are located, what kind of a charge they have, what kind of mass they have? Excellent, excellent. The electron is in that electron cloud. So we've got, we're going to call this little E minus for electron. So this is where your E minuses are. Okay, and the proton and the neutron are in the nucleus in a center. We can call this little P plus for proton and an N0 for neutrons. So protons, and your neutrons are there. Excellent. Electrons have a negative charge, protons have a positive charge, neutrons have no charge. Excellent. What about mass? Look at the symbol. Electrons have, yes, essentially no mass. That doesn't mean they really are massless. It's just so small compared to protons and neutrons that for the purposes of significant figures, it's essentially 0. Neutrons do contribute to mass, so they have a relative mass of 1. And protons have a relative mass of 1. Excellent. So electrons contribute to charge, but not mass. Protons contribute to charge and mass, and neutrons contribute to mass, but not charge. Excellent. And this is where they're located. So this is all from chapter 2. Everybody feel familiar with this? Feel like, oh, yeah, I know how to do that. At least a few of you, I hope. Okay. One new thing we're going to put here, because these are both contained in the nucleus, we will call them nucleons. Let's see if I can write sideways here, if that would be too weird. Wow, that was weird. Okay, never mind. Nucleons. Because they abide in the nucleus. And we also learned in chapter 2 that the same element can have different isotopes. What's an isotope? Like, for example, we could have the carbon-11 isotope, the carbon-12 isotope, carbon-13, and the carbon-14. They would all be carbon. But what does this little number in the top left-hand corner mean? That's the mass number. Okay, excellent. Now they're all carbon, which means which of these defines your element? Which of these is going to define it as being carbon? Yes. Yep, that's exactly right. Same atomic number, that's what makes it carbon. An atomic number is the number of protons. So elements, or atoms, I should say, not elements, because an atom is the smallest piece of your element. So atoms with the same number of protons, that's what defines it as being carbon, for instance. Carbon has 6 protons, so each of these would have 6 protons, but different masses. And where would that different mass come from? Different number of neutrons, because the neutrons will contribute to the mass, but not to the identity, because the identity comes from protons. So for instance, carbon 11 then would have how many protons and how many neutrons? If by atomic number is the number of protons that defines the element, you just look on the periodic table. Close, no, because 11 here has got to be the total mass. So that's going to be the total sum of both of your protons and your neutrons. If you look at the periodic table, here's carbon right here. Oops. Is that too small for you guys to see? Yeah, it's number 6. It has 6 protons. So carbon by definition has 6 protons. Each of these you can have 6 protons. 6 protons, 6 protons, 6 protons. Okay, so then how many neutrons would carbon 11 have? 5. 5 neutrons. What about carbon 12? How many neutrons does it have? 6 neutrons. Carbon 13, how many neutrons does it have? 7. And then carbon 14 would have 8. So note, always the mass is just the sum of your protons and neutrons. 6 plus 8 is 14. 6 plus 7 is 13. These all had 6 because it was by definition carbon. And then you could deduce, based on the mass that was given, how many neutrons each of those must have had. Is this coming back? Coming back to you guys? A little bit? Section 1 of the in-class activity sheet. And again, these usually end up stacked here. You should actually see this as P with a 244 on top and a 94 on the bottom, but it turns out Word is really difficult to make that work the way that I want it to. So they're offset, but they shouldn't be. The number in the bottom left is actually your atomic number, which we often don't include because it's defined by the element. So I could just look up plutonium and know that it's 94. But for the purposes of nuclear chemistry, it'll be helpful to include that number. It'll just be a little bit easier. And then the one on the upper left is your mass. Okay, so Joyce, hang on a second. Looking here at your periodic table, we see 6C 12.01. Then this is telling you, by the atomic number, it's telling you that it has 6 protons and that the average mass of all carbon atoms weighted for abundance is 12.01. Yeah, so again, because most carbon is carbon 12, but you've got a teensy bit of carbon 11 and a little bit of carbon 13 and a teensy bit of carbon 14. You add all those together, weighted for abundance, and that's where you get this average mass. So that's what we're looking at. Good, I'm glad you said something. Okay, so for section 1, how many nucleons? And remember, nucleons are protons plus neutrons. Or in other words, since that equals your mass, your nucleons are your mass. So for 244.94, this is plutonium. I'm going to have 94 protons, because that's given by definition. I have 244 total nucleons, because that's my mass. And that means that my neutrons must be the total mass, or the total number of nucleons, subtract my number of protons, and I should get 150 neutrons. Does everybody feel comfortable with section 1? We've done something similar back in chapter 2, but doesn't hurt to look at it again. Excellent. Okay, this gives us a starting point for nuclear chemistry, because the way that nuclear chemistry is different from all the chemistry that we've covered so far is that nuclear chemistry is chemistry that occurs in the nucleus. That's why they call it nuclear chemistry, okay? In the nucleus. And so it helps to know how many protons, how many neutrons, what is going on, what exists in the nucleus when we look at nuclear chemistry and nuclear reactions, okay? And what we find is that the heavier this nucleus gets, the more and more protons and neutrons we pack in here, then the less stable it becomes and the more prone it is to falling apart. Additionally, we'll find that there's kind of a nice ratio of protons to neutrons that we like to see. At the low end, you'll see about 1:1, which is why carbon-12 then is the most stable, because you've got the same number of protons as neutrons. At the high end, you know, masses, atoms with something like 100 protons, that it'll help to have about 1.5 neutrons for every proton. So the ratio of protons and neutrons seems to be important, but it's not something that's super well understood. We can kind of predict what might be stable and try to explain why that might be the case, but it's not super well understood. So if anybody wants to go into physical chemistry and study nucleuses, then there's certainly room for understanding more about what's going on here. It's kind of exciting. But essentially what we have is nuclear reactions that are going. If you have an unstable nucleus that has a poor ratio of protons to neutrons, or maybe just has too many protons and neutrons, then it will become radioactive and it will decay at some point in time. So that's nuclear chemistry. So nuclear reactions, there's 5 things that you need to know about how nuclear reactions are really different from chemical reactions. And the first is, like I've been saying, it involves the nucleus. I'm just going to copy and paste this list from your lecture notes. Involves the nucleus. All of the other reactions that we've covered so far focus on electrons, right? The electrons on the surface of the atom, those are what's doing the reactions. That's what's different about these ones. It's everything that's going on in the nucleus. The next thing we'll discover is that different isotopes react in different ways. So carbon-12 is really stable. It's not radioactive really at all. Carbon-13 is pretty stable. Carbon-14 will decay into carbon-12. So carbon-14 is radioactive. Whereas carbon-13 is stable. Carbon-11 will also decay, and it'll decay to form, I think, nitrogen. So it's also radioactive. So, and that just has to do with the ratio of protons to neutrons that I have in my nucleus, okay? You'll never have to predict which isotopes will react, but I do want you to know that different isotopes do react in different ways. Next, this is important, rate is not dependent on, it's completely unchanged by temperature, pressure, and catalysts. So these are things that affected our collision theory that help us understand how chemical reactions occurred, and you could change and speed them up. But they don't touch nuclear reactions because none of these are actually going to touch the nucleus. The nucleus is well shielded by those electrons. So they're completely unaffected by that. Nucleus decays whether the atom is in an elemental form or in a compound. So if I have elemental carbon, like a little hunk of coal, right? Or if I have sugar, let's see, draw a picture of sugar. I have sugar cane. See, we have sugar cane, which has carbon in it. If I have a carbon 11 atom here, it will decay. If I have carbon 11 atom here, it will decay. Again, this is because the nucleus is shielded from everything else. It's going to do what it's going to do regardless of what it's attached to. So if my carbon is in a sugar compound, it doesn't matter. It will still decay and form something else, whether it's in a compound or just in an elemental form. And then this can be really interesting. Energy levels are huge, huge. So a gram of uranium, 28 million times more energetic than a gram of gasoline. So you can see why nuclear reactions might be really helpful to tap in order for energy production to go forward with fewer emissions, right? Because it's going to take 28 million times as much gasoline, which is going to include 28 million times as much carbon dioxide as a byproduct, assuming that's the only byproduct that you get from combustion of gasoline, as opposed to 1 gram of uranium-238, which is going to yield 1 gram of radioactive material that needs to be disposed of afterwards. So much cleaner by comparison, just because on a mass basis, it's so much more energetic. Does that make sense? Oh, I'm sorry, Robin, you asked why, and I wasn't paying attention to when you asked that question because I was looking on my screen over here. Did I answer your question in the course of that little mini lecture? Or if you could expand on the question. Oh, why do you have the energy levels? It's because actually gram of gasoline doesn't come from the gasoline being nuclear unstable. It comes from chemical reactions, right? So a gasoline is C8H18, and it undergoes this chemical reaction where it combines with oxygen to form water and carbon dioxide. And so here's your energy level for C8H18 and oxygen, and here's energy level for water and carbon dioxide. And so you get this measurable energy output from this reaction. But this is a chemical reaction, right? The carbon remains carbon. It's not an unstable carbon necessarily. It's just a slightly more energetic arrangement of atoms and then a slightly less energetic arrangement of atoms. So as a chemical reaction, the carbon atoms themselves are not changing. Whereas if you have uranium-238 and it undergoes a nuclear reaction, it's because the energy level that binds that protons and neutrons together in the nucleus are massive compared to the energy levels that bind electrons together at the surface. So because this is a chemical reaction and this is a nuclear reaction, like I'm fundamentally changing what I have. I might end up with thorium instead of uranium. Oh, okay, no, good question. Sorry. C14, so the gasoline here is just carbon, and almost all carbon is carbon-12, right? The carbon-12 reaction. And so, and again, it's on the surface, it's not in the nucleus. Carbon-14 is radioactive and it decays to carbon-12. And, you know, I'm not sure. My guess would be that because uranium is so much bigger and heavier, that there's more of that nuclear energy to be released by the reaction of uranium. I'm actually not a nuclear chemistry expert, so I don't know, relatively speaking, how much extra energy is released when carbon-14 decays versus when uranium-238 decays as a nuclear reaction. That's a really good question. I've never actually looked at this. We do know that this is naturally occurring. This is what we use in carbon dating to determine how old something is, because the amount of carbon-14 in the atmosphere hasn't changed, but then it becomes fixed and decays over time. Anyways, That's a really good question. I'll have to look at that. But yeah, so gasoline then is a chemical reaction. Uranium decomposing is a nuclear reaction, and that is these two verses. That's why this has such a much higher energy level, because we're looking at arrangement basically of electrons on the surface and how they're bound together, and this is arrangement of protons and neutrons in the nucleus and how they're bound together. All right, that is going to be it for today.